when someone says -1 is equal to the log base 7 of 1 over 7, what they're saying is 7 to the power of -1 is equal to 1 over 7. And again, is that true?
Yes.
Yeah. So it must be that -1 is indeed the log base 7 of 1/7. These things make sense? Happy so far? Let's do a few examples translating this around. So let's see, pi to the power 3 is equal to 1. How could you rewrite that in log form instead of exponential form? Let's see, let's just try to match up symbols.
Log base pi 3.
Okay. Log base pi of what?
81.
3.
Of whatever this is equal to 3. So maybe a few words of translation are in order. So this pi is the base of the exponent. Right here, it's the base of the logarithm. This 3 is the thing in the exponent. And after you translate to log form, the thing in the exponent is just the thing on the other side of the equation. Finally, the thing right now that's on the other side of the equation is now inside of the log. What do people think about that? So I guess there's another question, right? This is the same as that. Those are the same expression. Does one of those, if you wanted to like solve for the variable m, was that a good thing to do or a bad thing to do? Did we make it more like we have solved for m or less like?
Less like.
Less. Okay, so it's not always the best thing to do, but that's okay. Here's another one. What do you want to know? E raised to the power of x is equal to 9. What happens when you rewrite that in log form? And maybe we'll even just translate some things around. What's the base of this exponent? Yeah.
E, which is 2.
E, which is 2.7 something. Somewhere around 2.72. And the explanation for why that's the right thing to call E is in an extra credit, which involves some ideas coming from calculus. So this will become the log base E. And what should go inside of the log? 9 is equal to the other symbol in the expression. Have we just successfully solved for x? Yeah, so that's nice. When you see an equation in exponential form and you would like to know what's in the exponent, the answer is translated into a logarithm. X to the power 4 is equal to 81. Well, same questions. What's the base? X. So, when you translate this into log form, you will end up with log base x of, yeah.
Can't you write that as natural log 9 equals x?
Yeah, in fact you should. Thank you for pointing that out. Yeah, because right, ln means exactly log base E. And in fact, you should make that substitution. You have a name for the logarithm with base E. It's ln. And additionally, many of your calculators will just have an ln button. Okay, nice. So log base x of what should go in the parentheses? 81 is equal to? Have we successfully solved for x by doing that? No, right? In some sense, we made a loss. How would you actually want to solve that equation? You should take the fault for each end. So the takeaway here is translating between logs and exponents is often useful, but you know, you should think about what you're doing. Let's think about the other side. The translation goes back both ways. Log base pi of 3 is equal to m. What happens when you rewrite that in exponential form? Let's see, what's the base?
Pi.
Pi. What's the thing on the opposite side of the equation from the log?
M.
So it's pi to the m is equal to
3.
3. Log base x of natural log of x is equal to 9 becomes e to the 9 is equal to x. Log base x of 4 is equal to 81 becomes x to the power 81 equals 4. People feel pretty good about that? Nice. So, a lot of the time, if you want to evaluate something involving a log, you just have to resort to a machine. And that's kind of not surprising, right? If I ask you what, like, pi to the power e is, you're going to use a machine. The machine is using ideas from calculus to come up with approximations. But even if you knew those means, you probably wouldn't want to do them by hand anyway. So you do need machines to do a lot of calculations, but not all calculations. Let's try to evaluate some just by hand. And let's do it by trying to set up an equation and solving it. So log base 4 of 42, let's try to compute that. And here's how I'll compute it. That's the thing I want to know about. I'm going to give it a name. I'm going to make up a variable name to call the log base 4 of 42. What variable name would people like?
Any variable name?
Yeah. I don't.
X.
X. Okay. I see you also lack creativity, but you are decisive at least. There's nothing to that. So there's an equation now. Log base 4 of 42 is equal to x. I want to know what x is. Do you think you could rewrite that in exponential form now? Yeah, you could rewrite in exponential form and get 42 is equal to 4 to the power of x. Does that look like a type of equation that we solved, well, the last actual lecture on Wednesday? Yeah, how did we do it? Do 32 and 4 have like, are they powers of the same thing?
Powers of 2.
They're both powers of 2. 42 is, I think, 2 to the 5th. So you get 2 to the 5th is equal to 2 to the 2 to the x. So 2 to the 5th is equal to 2 to the 2 times x by exponential laws. So, what is x? 2.5. X is 2.5 or 5 halves. I'll leave it as 5 halves. Nice. So let's just write down the conclusion. So that means the log base 4 of 32 is actually 5 over 2. And if you have like a machine handy, that's a good way of checking that you're inputting things into your machine in the correct way. Nice. Do you guys want to do the next one? Log base 5 of 625?
Sure.
Yeah, do it. I suggest is a good place to start listing out some of the powers of 5. Cool. So what are you getting?
X equals 4.
And x is itself, presumably you like decided the name of this was x. So really the actual answer is just 4. How many people want to see that discussed in more detail? Cool, let's do it. So if we're going to use the same strategy as this previous one, then I guess it must be that 625 and 5 have like a common base. They're both powers of the same thing. And 5 is 5 to the 1 is prime. So 5 is the only choice. So let's try to write 625 as a power of 5. We need to use do to employ this strategy at all. Let's start listing powers of 5. What's 5 to the 1?
5.
5. 5 to the 1 is 5. So what's 5 squared?
25.
25. So what's 5 cubed?
125.
125. Right, you just have to keep on multiplying by 5?
Correct.
So if you want to do that again, well, I guess the numbers are getting big enough and you might not have the powers of 5 memorized past 125. To get 5 to the power 4, 5 times 5 is 25, carry the 2. 10, it's 12 with you carry the 1 over. 625. Cool, so log base 5 of 625 is really the same as the log base 5 of 5 to the power 4. We're pretty happy. And now we can play the same strategy as above. We can say, well, let's just give that a name. We want to know what it is. We can give it a name at least. Let's call that, I won't call it x. X already has a job. I'll call it y. X is the variable from the last exercise. So we'll take that. We'll rewrite it in exponential form. So you write it exponential form. To get 5 to the 4th is the same as 5 to the y. But is the function 5 to the x a one-to-one function? Yeah, so the only way 5 to a thing is the same as 5 to another thing is if thing is the same as other thing. Nice. People feel all right about that? Cool. Let's do more. So part of the point of inventing inverses to functions is they're what you need if you want to solve equations that involve that function. So here's an equation we couldn't come up with a solution to last time. 5 to the x is equal to 7. All right, there are no common bases we can take advantage of, so we're just kind of screwed on that one. On the other hand, what do you get if you just rewrite this in log form? Let's see, what's the base? 5. So it'll be 5. So log base 5 of, what's the thing on the other side of the equation?
7.
Log base 5 of 7 is equal to x. Hey, cool, does that just solve for x? Yeah. But of course, you might actually care about how big that number is. And I guess right now, using what I know, well, I know that that number has to be bigger than 1, because 5 to the 1 is 5, which isn't big enough, but it's less than 2. So the actual value that this will take will be somewhere between 1 and 2. If I want to do better than that, I'm going to bust out a machine. The thing I will elect to use is just going to be the Google calculator. I don't want to try to give a live demo of figuring out how everyone should use their own handheld calculators all at once, because I wouldn't be able to help anyway. You can use Google to find your calculator's manual just as well as I can. Let's compute. Let's try to compute. The log, oh goodness, will Google actually, yeah, there it is. The log of 7 with a base of 5. Okay, no. Let's compute Gesundheit. The log base 5 of 7. There it is. It says it's somewhere around 1.2. Oops. People feel pretty okay about that? So I think what I'm going to do is I'll talk through one of these two solutions, and I'll leave the other one for you guys to do. Which one do people like me to talk to? People want me to talk to the first one? Or do people would rather I talk to the second one? Okay. Non-standard. Let's talk to the second one. Let's try to solve the equation 3 to the power x squared, with x squared all in the exponent, is equal to 8. So let's see, it's annoying that the x squared is in an exponent, right? But I know how to get things out of the exponent. I just need to rewrite it in log form. So let's rewrite this in log form. What's the base? 3. So the log base 3 of the thing on the other side of the equation, 8, is equal to the thing in the exponent, x squared. Okay, cool. Well, I guess we should reflect on what we just did. Is that at this point completely solved for x? Is it closer to being solved for x? Sure is. How do you solve that for x now? Take the square root of each side. So I'll get x is equal to the square root of the log base 3 of 8. Have I left anything out? What have I left out? Plus or minus? Although, why, you can't literally plug negative numbers into a log, so let's take a moment and think whether this is actually legal. Let's look back at the original expression. Can I plug in a negative number for x and have something that makes sense? Yeah, so both are valid solutions. Those of you who are already punching away on your computing machines, what is the square root of the log base 3 of 8?
1.8. Oh wait. Log was 3. 1.89.
Somewhere around 1.89.
But the square root of that is 1.28.
Oh, okay, you didn't have the square root yet. Okay. Oh, I should still have the plus or minus. If I can get a number somewhere around that? Cool. Here's another one to solve. 3 to the x to the power 2, with parentheses as a parent there, is equal to 8. And maybe I'll give you guys a choice here. I can keep talking, or you guys can take a moment to discuss with each other. Do people want me to just keep talking? Okay, then I keep talking. 3 to the power x to the power 2 is equal to 8. And we want to solve that part, so we want to get x on its side. Let's just try something. What would you like to do to that to try to get x on its own?
Log of both sides.
Well, the thing on the outside of the complicated side is a squaring. How do you want to do squaring?
Get it out of the way first.
Yeah, get the square out of the way. So how do you want to do that square?
Be 9 to the x, or be 9 to the 2x.
Ah, cool. Okay, so there are two strategies. Here's one of them. Right, 3 to the x squared, that's the same thing as 3 to the 2x, or 3 to the 2 to the x, or 9 to the x. Oops. Yeah. That seems like a good choice. So you can just simplify this before you even start. Get an equivalent equation. 9 to the x is equal to 8. Is that now easy to solve using log techniques? What do you get when you rewrite that in log form? Oh, God damn it. No, that's an x. That's right. 9 to the x is equal to 8. It's hard to see from this angle. The x looked like a 2, which I could see me doing that. What do you get when you rewrite that in logarithm form?
Log base 9 of 8.
So there's one solution technique. Use exponential laws to simplify, because one side is only complicated because it has complicated exponents, but you have rules for how exponents should behave. So if you just use those rules, you can simplify before you start. How many people are just like that first step of simplifying set in more detail? I saw some people who looked upset. People want me to talk about the first step in more detail. Okay. Let's talk about another solution technique, because right, that was a good idea. But you can also just brute force your way through things without a good idea. So this is how like a human being should solve it, but let's solve it the way a computer would try to solve it.
You could like take the square root of both sides.
You could start by taking the square root of both sides. Because the side that looks complicated is complicated because there's a square. So let's get rid of the square. So here's another solution technique. 3 to the x to the power 2 is equal to 8. Could become 3 to the x is equal to plus or minus the square root of 8. Because right, when you want to do a square with a square root, you get a plus or minus. Is 3 to the x ever negative? No. So is the negative solution actually valid? No. So just plus. And maybe I'll even simplify that square root of 8. That's the same thing as 2 root 2. What do you get when you rewrite that in log form?
Log base 3 to the square root 2.
These two, Chris, what's wrong with you? Those two answers on their face look kind of different. But if you actually like compute the right-hand side of the blue one, do you get the same thing?
Yes.
And this is hinting at some algebraic laws for logarithms that we'll actually do in detail next time. 0.946. Nice. Cool. So again, like the reason to care about exponentials is because they can model things like population growth. The reason to care about logs is they undo exponentials. Let's think about a population growth problem. So again, population triples aboard the USS Enterprise. Has population modeled by the function p of t is equal to 2 to the t. The population doubles every hour. The life support systems on the ship will be overwhelmed once the population hits 30,000 triples. How long does the crew have in order to solve this problem? Let's see, when will the... Let's try to write this as an equation. Population is equal to 30,000. Do we have a function that gives the population at any given time?
Yeah.
Yeah, it's 2 to the t. We write as an equation. 2 to the t is equal to, how big is the population when something bad happens? 30,000. Does that look like an easy equation to solve? Well, at this point, I hope it does, right? We just need to rewrite it in log form. What's the base of the log? 2. So this will become t is equal to 2 is equal to, t is equal to the log base 2 of 30,000. And because you probably care about like approximately how many hours that is, what is the log base 2 of 30,000?
14.87.
I'll just, that's enough digits for me. I just should round up to 9. Cool. So, two takeaways here. One, that's not so big a number. Right? That's only like 15 hours. 30,000 is like a really big number. So this is telling you two things. Exponentials grow real fast. And logs, while they keep on growing, get real slow. Log base 2 of a really big number just became a number that's getting big, but really slowly. And I guess it also tells you, yeah, the crew has 15 hours to solve the problem. Okay, so let's explore some subtleties for a moment. Here's one. Let's try to use the tricks we know to evaluate the log base 2 of negative 3. Let's try to do that. And we'll do it using the techniques we used at the bottom of the previous page. I'll give this a name. I'll call it, I don't know, Z. And just like last time, I'll say, well, I want to know what this thing Z is, and here's how I'll do it. I'll rewrite that equation in exponential form. Two to the power of Z equals negative 3. So you need to come up with a power of 2, which is equal to negative 3. Is 2 to a power ever negative? Does that equation have any solutions?
No real ones.
No real ones. There's some subtlety. You can figure out what. Well, there are two weird things that happen once you start evaluating logs at negatives or complex numbers. The exponential function, if you allow for complex things, isn't actually one-to-one. There are some weird things that happen that I won't do in this class. And so, like, you can get an answer to that by thinking about complex algebra on complex numbers. But you'll find out that you can't pin down a single solution. This actually has infinitely many solutions, which all differ by multiples of 2 pi I, which is something I will not explore in this class. But let's remember what this means. So let's look back at the graph of the log base 2. What's the domain of log base 2? By looking at that graph. 0 to infinity, including or excluding 0. The domain of any logarithm is 0 to infinity. And this is why. If you try to plug a negative or 0 into a logarithm, you'll end up saying an exponential is equal to something that an exponential can't be equal to. Again, let's try to evaluate the log base 1 of 4. And so let's play the same game. So I want to say, well, let's give that a name, alpha. So you'll rewrite that in exponential form. You'll say, well, that means 1 to the power alpha should be equal to 4, and I need to solve that equation for alpha. What power of 1 is equal to 4? Well, there isn't a solution to that, is there? What's 1 to the alpha always equal to? 1. So again, we see no solution. And in fact, could that 4 have been basically anything and we would have been in trouble no matter what?
Correct.
Yeah, I guess it would be different if it were 1. But let's try to think about what we would need to solve in order to compute log base 1 of 1. We would wind up needing to solve 1 to the alpha is equal to 1. What are the solutions to that equation? Everything. So the log base 1 of x most of the time doesn't exist, and if you try to think about the log base 1 of 1, you get that should be everything. That's like really bad. So the logarithmic function will only make sense when b, well, is not equal to 1, and I guess b had better be bigger than 0 too. Those are the only bases you're allowed to use. You're allowed to use positive bases, but not 1. 1 is bad. Cool. Yeah. Let's do some graphing. And let's even do this really quickly. So we know that the only valid bases are positive numbers other than 1. And let's think about what the graphs will look like in general. What does b to the x look like when b is, say, bigger than 1? Well, that's like a hard question to ask. Like you would make like hand motions, but since you're looking at me and I'm looking at you, our hand motions will like be opposite.
Here, I got you.
So it'll be something like that. So there's the case b is bigger than 1. if b is less than 1, but still bigger than 0, otherwise you can't think about that exponential function. You got that graph. Are both the pink and the blue function, are they both 1 to 1? All right, so that means we can involve them. And I'll do it quickly, and then maybe we'll gesticulate at why this is correct. So there's the log base b of x when b is bigger than 1. All right, so all I did is I took the structure of the pink and I flipped all the xy coordinates. Maybe I'll keep track of one thing. What's the coordinate of that x-intercept? Be 1, 0. Why was it 1, 0? Let's go over here. What is the location of this y-intercept?
0, 1.
0, 1, because b to the 0 is 1. On the other hand, there's the log base b of x, when 0 is less than b is less than 1. And let's read some things off from the domain, from these pictures. What are the domains of those functions? On either the pink or blue graph, what x values do you see? Do you see any negative x values? Do you see 0 as an x value on the graph? No, there's a vertical asymptote at 0. So the domain is apparently only things that are bigger than 0. What's the range of the logarithmic functions? What y values do you see on those graphs? Oh, so all real numbers. Or if you like interval notation, negative infinity to infinity. Log base b of x, where is its x-intercept? It's an x-intercept, so y better be 0. Where are the vertical asymptotes of those logarithmic functions?
X equals 0.
At x equals 0. And I guess you see that they're like only one-sided vertical asymptotes.
Why do you keep saying they're like technically one-sided if when they go on the other side, it's not like they're going to go downwards?
Well, in this case, there's like nothing on the other side.
Oh, okay.
Yeah, that's all I mean this time.
Okay.
Right, so exponentials have like a one-sided horizontal asymptote. And that when the exponential goes off to plus infinity, the blue one has y coordinate going to 0. But as x goes to negative infinity, the blue just gets big. So yeah, so this has like only a one-sided vertical asymptote because the domain isn't even big enough. You can make the domain bigger by doing some trickery. So let's see. I think we'll get back to thinking about the graphs of the various log functions as we go on. I encourage you to like do that on your own time. So on your own time, sketch those graphs by looking at a computer and see how they compare. More on that later. So let's do this. So let's think about domains of how to find domains of logarithmic expressions where there's something interesting going on inside the parentheses. So let's try to compute the log base 2 of, I don't know, 3x minus 4. And we'll think of this the same way as we computed domains of square roots. What things can you see inside of the parentheses in a logarithm? Are you allowed to see negative things? Are you allowed to see 0? Are you allowed to see positive things?
Yeah.
So in order to compute the domain of this, we need to solve an inequality. I'll just find the domain. You need to solve the inequality 3x minus 4 is strictly bigger than 0. Is that like a super easy inequality to solve? Yeah, it's one that you can do without even playing this game where you solve equality first and then you one. Right, you can just add 4 to both sides and then divide by 3. So in interval notation, I guess that would be 4 thirds all the way on to infinity. People feel good about that? So I think with the time remaining, well, what the hey? Let's find the x-intercept too. How do you find the x-intercept of a thing?
Y equals 0.
You set y equal to 0. So if you want to find the x-intercept, you need to solve log base 2 of 3x minus 4 equals 0. And you need to solve that equality. Does that look like an equation right now that is in logarithmic form? Yeah, it is, right? It's literally log is equal to a thing. So do you think we could rewrite it in exponential form and have something that looks nice? 3x minus 4 is equal to 2 to the power 0. But what's 2 to the 0? Good. And is that now a super easy equation to solve? I guess add 4 to both sides, divide by 2. No, add 4 to both sides, divide by 3. See, I'm looking at you, so I forget what all the numbers are. Add 4 to both sides. 3x is equal to 1 plus 4 is 5. X is equal to 5 thirds, so you see an x-intercept at 5 thirds, comma 0. And I think there's enough time to do one interesting domain computation. So I'll give you guys a choice. Domain of the log of 4 minus x squared, the domain of log of a rational function, or the domain of the log of an absolute value. The one with the square? The one with the ratio? I think that's a plurality. Cool, so let's solve this. Let's find the domain. So in order to find the domain of this thing, what inequality do I need to solve? What types of numbers can appear in logarithms?
Positive.
Positive. And I really mean positive. 0 is forbidden. So I need to solve the inequality 1 plus x divided by 1 minus x is strictly bigger than 0. And because I may or may not have time to finish, let's outline the steps that you need to do to solve this. So first, solve equality. 2, find vertical asymptotes. And 3, do this between and beyond game. So now that we have the steps written down, let's actually go through it. When is that black function equal to 0? What do you get when you set that equal to 0 and solve for x? I think you just get negative 1. It's when the numerator is 0. That's the only way you can get 0. Where's the vertical asymptote? 1. So now you need to play the check between, check beyond game. And maybe we'll even do that by, all right, so there's negative 1, there's 1. What's a number that's more negative than negative 1? Negative 2. Maybe I'll go for something easier, negative 25 trillion. Because then I'll get 1 plus negative 25 trillion, that's basically negative 25 trillion, and 1 minus negative 25 trillion, that's basically plus 25 trillion. What's negative 25 trillion divided by 25 trillion? Negative 1. Is that bigger than 0 or less than 0? Less than. So, those are bad. Without doing any computations, what's your intuition? Will numbers between 1 and negative 1 be good or bad?
Bad.
I think they'll be good. Let's plug in 0, see what happens. What's 1 plus 0? 1. What's 1 minus 0? 1 divided by 1 is? 1. Is that bigger than 0? Yes. Yeah, so these are good. So the end solution will be an interval from negative 1 to positive 1, and neither will be included, because you won't include the vertical asymptote because you never do. And you're solving strict inequality, so you won't include the solution to equality. Cool. Well, I'm over time. let's see. So hopefully everyone who wants to give me their points back stuff for the midterm has. Is there anyone who wants to like visit with their midterm? I won't give it to you yet. Anyone who wants to see their midterm?
No, thank you.
Okay, cool. Huh? Oh yeah, thank you.